Right. So with that, we are starting. Coming to the physical system, which are the physical system we are considering? Physical system can be mechanical translational system, or mechanical rotational system, or mechanical system can be an electrical system or electromechanical system, or it can be an electronic system or a political system, or so on, liquid level system, thermal system. So all if you want to control any particular system, the first step is mathematical modeling. So we are trying to discuss mathematical modeling of physical system in this particular class. Okay, so let us start with, so how many ways you can model the physical systems as we discussed in our last classes? What are the different ways you can model physical systems? Tell me.
Mechanical, electrical.
No, coming to the different ways of modeling physical systems.
Sir, block diagrams.
Block diagram is a pictorial representation of physical system. So coming to the modeling of physical system, there are two types or two ways we can model. One is transfer function. Another one is what? State space representation. That's what I said, right? Any physical system can be modeled into two forms. One is transfer function form. Okay, so transfer function form, and another one is state space form. So transfer function for which type of plants we can model? This is by using, for what? We will model the systems. If the system is a linear time invariant system, then we can model it in transfer function. But all the real-time systems are non-linear time varying systems, is it not? Okay, so when they are non-linear time varying systems, we can model by using state space form. So the first modeling is transfer function. So how do you define transfer function? Transfer function is the ratio of Laplace transform of the output to the Laplace transform of the input, considering all initial conditions to 0. Okay, so we define transfer function is a ratio of Laplace transform of the output to the Laplace transform of the input, assuming all initial conditions 0 or considering all initial conditions 0. So what do you mean by it? We'll be seeing this little later. So now, for any physical system, we can give an input called reference signal or reference input. The output of a plant is called controlled output. So C of t. Okay, C of t. So Laplace transform of R of t is R of S. So Laplace transform of C of t is C of S. So where L is the Laplace operator. So now transfer function now for this particular plant, it can be written as C of S by R of S is a standard notation throughout the world where you go. The control system point of view, it is a standard notation. G of S is equal to C of S by R of S. So if you, this would be any physical plant like what we discussed now. So it can be of a mechanical system, it can be of electrical system, it can be of electromechanical system or something. So So the transfer function is a ratio of Laplace transform of the output to the Laplace transform of the input. R means reference signal and C means controlled signal. Okay. So electronics point of view, we talk about signal. Okay. So we assume initial conditions 0. So what do you mean by assuming initial conditions 0? Now, if you take an electrical system like a simple RLC, okay, just a second. Hello. What department కి వచ్చానమ్మా? Yeah. So now, if you try to take okay, so if you try to take now reference input R of t, this is R, L, and C, and output is like controlled output is C of t, right? R input is a voltage to this, and output is also voltage across the capacitor. So what we are interested in is, if you give the input signal all of a sudden, if you apply a input voltage, let us take 10 volts, how would be your output is changing is what I am interested in. So I want a ratio of Laplace transform of output by voltage across capacitor by Laplace transform of input Vi of S. So this is what I am trying to find it out. So the definition says like it is a ratio of Laplace transform of output to the Laplace transform of input, assuming all initial conditions 0. So what do you mean by initial conditions 0? Right now, to the capacitor, right, do we have any initial voltage? Is that the response of the capacitor changes with initial voltage across the capacitor? Is it not? If no, if there is some initial current in inductor, initial voltage across the capacitor, that need to be added, right? Okay, so your output may change when you consider your input, right? Initial conditions, right? But here, for simplicity purpose, we can neglect them. There would be initial current in the conductor, in inductor. There would be an initial voltage across the capacitor, but these values would be changing. Okay, would be changing when you apply input and your output when you added up these things. So, but why we neglect these quantities 0 is the initial conditions or the initial current in inductor or the initial voltage across the capacitor would be constants. So when you neglect them, it will become very simpler equation for us. Okay, and because they are constants, they can add it up at any moment in the analysis at any time. Is that understood, all of you? Transfer function is understood. It's a ratio of Laplace transform of output to the Laplace transform of the input, assuming all conditions 0. So why we assume all initial conditions 0? Tell me.
To simplify the equation.
To simplify the equation. That is the first reason. The second reason is these initial conditions are constants. Yes or no? So they can add it up later in the analysis. Okay? Yeah, that is the reason. Right. So now, why Laplace transform? So by use of Laplace transform, we can convert many common functions into algebraic functions of complex variable S. If you take sine omega t, then omega by s square plus omega square is what we say. Our exponential function e power minus at means 1 by s plus a, Laplace transform of it. So here s is a complex variable or complex frequency, which can be sigma, which can be written as sigma plus j omega. Right. Now, if a third order or fourth order differential equation is given to you, how do you solve the differential equation?
Applying Laplace and again inverse.
Other methods other than Laplace transform, what are the other methods you know to solve differential equation? Do you have any numerical methods? Oh God.
We find the complementary solution and a particular solution.
A solution of differential equation is complementary solution plus particular integral. That is one way, right? But if it is second order, third order differential equation, then what happens? It becomes very difficult. Then what we do? We take help of Laplace transform. Is it not? Yeah. So now Laplace transform of differential. So Laplace transform of d by dt of x of t is s x of s minus x of 0, where x of 0 is the initial value. Correct, no? Right. Laplace transform of d square x of t by dt square is s square x of s minus x of 0 minus x dot of 0. What do you mean by this? Physical meaning here, anyone? Equation point of view, leave. But do you
The rated
physical meaning of initial condition? So x of 0 means what? Now if you are considering about electrical circuits, initial current in inductor and the initial voltage across the capacitor can be called as initial conditions, right? Similarly, x dot of 0 means what?
the rate at which x is changing when t is equals to 0.
Physically, yeah, physically. X of 0 is what I told. Similarly, x dot of 0. So now, anyone, you understand like what do you mean by x dot of 0, which is d by dt of x of 0? That does it exist? Do we really need to concern about it? If you are not able to answer the question, you can type in chat box also if you want to feel so. Anyone?
The rate of change of zero of a function with respect to time.
Rate of change of 0 with respect to time, correct. But physically, by considering an electrical system or mechanical system or any system, physical meaning or physically can you analyze or physical answer you can give. Now, x of t, now I am talking about mechanical systems with respect to mechanical systems. X of t is displacement. Dx of t by dt,
Velocity.
velocity, which we can write it as dv of t by dt, which is x dot of t. D square x of t by dt square.
Acceleration.
Acceleration. Right.
Sir,
So
in
we
the
have
terms of impulses.
So now d square
Sir, in the
or d cube x of t by dt cube. Rate of change of acceleration is called
Jerk.
jerk. Excellent. Jerk. So now we have terms like displacement, velocity, acceleration, and jerk. Now there would be, when object is, when it is, it is moving, it may have initial velocity. Right. So now you tell me now, what do you mean by x dot of 0 here in the case? Can you relate physically what I'm trying to give you?
Sir, in the terms of impulses.
Yeah. Right. So certain initial conditions. Now, can you generalize Laplace transform of d power n x of t by dt power n? S power n tell me. S power n. Array. Generalization.
Minus
S power n x of s minus
x of 0 dx of 0 by dt.
then
The derivative terms.
N minus 1. Derivative of n minus 1.
yeah. So it is s power n x of s, s power n minus 1 x of 0, right? So on up to x bar n minus 1 of 0, right? So where x of 0 is the initial conditions of the system. Now, when we are trying to obtain transfer function of physical system, what we assume? We assume
Initial condition 0.
all initial conditions 0. Why also I explained. So now let us try to take, this is a simple RC system, right? So if the capacitor is not already charged, then y of 0 is 0. This is the initial condition, meaning of initial condition, right? So now if I want to obtain transfer function of it, okay, now if I want to obtain transfer function of it, so now V is, if I consider it as a voltage, so then if I write, when we mathematically model electrical systems, we try to use Kirchhoff voltage law. So V of t or Vi of t minus R. Now if you apply the voltage, if it results in a current in the circuit, which is I of t, so minus Ri of t minus, tell me.
1 by c integral I of t dt.
I of t dt is equal to 0, right? So I am interested in what? Right. If I apply voltage, then how is the voltage across the capacitor is changing? Vc of s by Vi of s. I may be interested in this term, or I may be interested in this term. I of s by Vi of s means what? How the current in the circuit is changing when I apply voltage suddenly. So I can obtain two transfer functions. Is it not? So if I want this, straight away I can apply Laplace transform, right?
Yes, sir.
Right? No. Yeah, but if I want this VC of S, but we know that VC of S is what? Or VC of T is what? 1 over C integral I of T dt. Is it not? This is equation number 1. This is equation number 2. The output voltage, which is voltage across the capacitor, can be considered as VC of T is equal to 1 over C integral I of T dt. Correct? So I can write this equation as VI of T minus RI of T minus VC of T is equal to 0. So if I want the transfer function 1, then I have to, write only output terms and input terms. Correct? No? Right. So now if I apply Laplace transform of this to this equation, so VI of S minus RI of S minus VC of S is equal to 0. So I have to write a ratio which is VC of S by VI of S. But now I of S is an intermediate variable which resulted, in between, right? But when I write Laplace transform to the equation number 2, what I get?
VC of S in terms of I of S.
So VC of S is equal to 1 over C, yes, I of S. Is it not? Yes or no?
Yes, sir.
Right. And I'm assuming initial conditions 0. So I'm not taking initial conditions now. Correct? So I can write I of S is equal to what? VC of S, CS. Correct? No? So if I write equation number 3 and here, then what I will be getting? VI of S minus R. I of S is what? VC of S and CS minus VC of S is equal to 0. So now I can separate VC of S, no? So now tell me the ratio. VC of S by VI of S is
1 by 1 plus RCS.
1 by 1 plus RCS. So this is what the transfer function of a simple RC circuit. Okay, so transfer function, which is VC of S by V of S, it is what this. Correct? So now Laplace transform of integrals. The time domain integral becomes division by S in frequency domain, that we know. And calculation of transfer function means, this is what we can do. A S square X of S minus S X of 0 minus X dot of 0 is equal to C S phi of S. This is how we can do, and then we can get the transfer function. So now, if you have an nth order differential equation, okay, if you have a nth order differential equation, if a system is governed by nth order differential equation, a0 y of n plus a1 y of n minus 1 plus an minus 1 y dot plus an y is equal to b0 x, where here x is input, y is output. Input is also available in terms of differential term. Then when you apply Laplace transform of this, then the transfer function, this is a generalized transfer function. Okay, this is a generalized transfer function which can be written as b0 s bar m plus b1 s bar m minus 1 plus 1 up to b minus 1 s plus bm by a0 s bar n plus a1 s bar n minus 1 plus an minus 1 s plus an. Okay, so this is what the generalized transfer function. If you have a system, if it is governed by nth order differential equation. So is this understood now? Now, if the order of the denominator polynomial is greater than the numerator polynomial, then the transfer function is called proper transfer function, otherwise it is called improper transfer function. Okay, proper transfer function and improper transfer function. So this transfer function helps us in deciding the stability of the system. Okay, and time domain and frequency domain characteristics of the system, and response of our system for given any input. So that is what transfer function is. So now we will go ahead with step by step. Okay, right. Now, all electrical systems or electronic systems can be modeled by using three components like resistance, inductance, and capacitance. Is it not?
Yes, sir.
All electrical devices or electronic devices can be modeled by using three components: resistance, inductance, and capacitance. Can we replace transistor using its equivalent circuit? Yes or no? Small signal equivalent.
Yes, sir.
What is the model called?
Small signal model.
Small signal model, H parameter model, right? Okay. Similarly, any mechanical system can be modeled by using three components. One is mass, another one is spring, another one is friction. Okay, so we try to see. All right. Any mechanical system, the statement is any mechanical system is modeled by using mass, spring, and friction. Right. So now we will see individually. What is mass? So mass is considered as a property of an element that stores the kinetic energy of a translational motion. Mass is considered to be a property of an element that stores the kinetic energy of a translational system motion. Now M can be given by W by G, where W is what?
Weight.
Weight. G is acceleration of
Acceleration due to gravity.
gravity, which is 9.80 meter per second square. Now, translational motion. So, as the motion that takes place along a straight line is called translational motion. So, we are going to model mechanical translational systems. When you apply force, the motion that takes place is along a straight line. The motion that takes place along a axis is called
Rotational motion.
rotational. So our objective now, we are restricting to mathematical modeling of translational, mechanical translational systems. So the first property is mass. Right? Now, ideal mass. So when we consider ideal mass, means when you are trying to apply a force on the mass, definitely there is a opposing force which opposes the motion of the body. Is it not? That may be due to friction, right? Or that may be, or otherwise when you try to apply a force, there may be deformation in the body, right? So we are assuming now ideal means what? There exists no frictional forces and there exists no spring forces, or there are no elongation or compression in the body. There is no compression or there is no elongation in the body, right? So when when you try to model the mass, if you are applying a force F of t, then the body will be in acceleration. If the displacement, if it is x of t, then we will be using Newton's second law of motion, which states that summation of forces acting on a body is equal to the product of mass and acceleration. So F of t is the force applied, and there is no frictional force. So we are assuming that is no ideal mass, and there are no compression and deformation in the body. So F of t is equal to m d square x of t by dt square. So this is how we model mass, ideal mass. So is it all right, all of you? Then the next component is a linear spring. A linear spring is considered to be an element that stores potential energy. Linear spring is considered to be an element that stores potential energy. Right, the compression or deformation, the deformation which happens in the body when you apply a force can be represented with a spring. Now, when you apply a force F of t on this, there is a displacement x of t in the body, and this is proportional to the displacement. The applied force is proportional to the displacement. F of t is proportional to x of t, where f of t is equal to kx of t. This is how we model an ideal spring. So that the mass is not having any, so the spring is not having any mass or any frictional forces, is what assumption is. Right. There would be case like this also. Here, there are two bodies of mass m1 and m2. And this mass m1 and m2, there exists a deformation between these two bodies, which is represented by using a spring. Now, if I apply force here, right, so this mass moves here in this direction and the displacement is x1 of t. And when this mass is moving in this direction, definitely, is there any displacement in mass m2? There will be displacement in m2 or not, because this is the mass 2 is attached through a spring, right? Yes or no? So this body, when it is moving in this direction, there is an elongation in the spring, correct? But this side, what happens? Due to this, when m2 is moving in this direction, there would be here, if I consider k is the stiffness of the spring, right? So the displacement, if I apply force here F of t, and if I consider the spring K2, okay, if I consider this spring K2 is the stiffness of the spring between these two bodies, then the applied force is proportional to the resultant displacement. Is it not? You got this point?
Yes, sir.
Yes, sir.
So here, when this body is, when he is trying to move in this direction, so this spring force is in which direction? Opposite to the movement of m1, or it is in the same direction of m1?
It would be opposite to M1.
This is opposite to m1, right? And because m2 is connected to m1 through k2, so this, when m2 is moving in this direction, the spring force is in m2 direction, or opposite to m2 direction, or which direction?
In M2 direction.
Definitely, because there is a displacement in M2 that is due to spring only, no?
Yes, sir.
So
Yes, sir.
now, when we consider M1 and the forces acting on this particular body, so we try to write called a diagram called free body diagram, on which we indicate all the forces acting on a body. Now, if I consider M1, force is applied in this direction, but spring is attached to this body, so there would be additional force which will be opposing direction, right? Which is Fk2 of t. Is it not?
Yes, sir.
Right. So now, if I try to write, or if I try to model this particular mass, if I write Kirchhoff second law, sorry, Newton's second law of motion, summation of acting on a body is equal to product of mass and
Mass and
acceleration.
acceleration.
So this m1 is in this direction. So x1 of t is in this direction. So f of t minus f k2 of t is equal to m1 d square x1 of t d square x1 of t by dt square. Is it not? Mathematical model of physical system. Understood, no?
Yes, sir.
Now, there is nothing here, only M2. You know, this is connected to M2. So can you tell me the free body diagram of M2? Is there any displacement in M2 or not? Yes or no? Then that will be in which direction? X1 direction or opposite to X1 direction? This is pulling this side, no? Right. Now, is there any forces acting on M2?
Yes, sir. The spring force.
That will be in which direction? Along with X2 or opposite to X2?
Along x2.
Along.
Due to the K2, the spring with spring constant K2, it would be along x2.
So this is Fk2 of t, right?
Yes, sir.
Yes, sir.
Right. So Fk2 of t is equal to, is there any force acting on it? No, no, no direct. F of t is not directly acting on M2, right? So Fk2 of t is equal to M2 d square x2 of t by dt square. Is it not? Yeah. So why I am telling all these things means you have to understand the spring, you know. So here, you know, for M1 it is in this direction, and for M2 it is in this direction, right? So when we try to model a spring in this condition, f of t is k into the resultant displacement is what we try to take. Is it not? Understood now? The next one is, okay, so the next one is friction. The next one is friction. Yeah. So now, and you know what is friction, what is the advantage of friction and all. Right. If friction is not there, is that movement is possible?
No, sir.
So now this friction is of three types. One is viscous friction, one is static friction, another one is cooling friction. Right. So there is a body like this. So now I am trying to apply force. but there is something which opposes the movement of the body. What is that friction called?
Sir, can you once again repeat the question, sir, please?
Yeah, see, now I have a body like this. Okay. Right, I have a body like this. Right. So now I am trying to apply force on it.
Mm.
Okay. So I am trying to apply force on it. But you know, there is something which opposes the movement of the body. That kind of
Static,
friction is called
Static friction.
static friction.
static friction. So a retarding force which opposes the movement of the body when it tries to come in motion is called static friction. Correct. Now the body is in movement. If there exists any friction or not?
Kinetic friction.
Yeah. So there exists some friction. That friction is called viscous friction.
Sorry, sorry, sir.
Okay, that is called viscous friction. So that means in control system, we assume that the body is in the motion and we assume static friction is 0. So we talk about when body is in movement, the friction which exists is what we try to consider while we are modeling it. So that is modeled by using an element called dash pot. So what do you mean by this dash pot? There is a container. Okay, there is a container, and in which there is a piston moving in it. And this container is fixed with or filled with liquid. Okay, so this container is filled with liquid. Right. So now there is a piston like this in the container. So I am applying a force F of T on the piston. And there is a fluid inside, liquid inside. So the friction which exists here is proportional to the velocity of the piston movement. So F of T is proportional to d by dt of x of t. And we write the proportionality constant as B, which is equal to F of T is equal to B dx of T by dt. Okay? Is that understood?
Yes, sir.
So this is viscous friction. In mechanical systems, we consider viscous friction, which is related to the friction, you know, the thing which is there in the motion. There is one more friction is called Coulomb friction. So that also we assume it as, you know, it is 0 in mechanical systems point. Right. So now let us take, there is a mass damper system like this, which is shown in the figure. Now, to just model it, there is a mechanical system having a mass of m, and then it is attached to a wall through a frictional thing, and B is what is a frictional constant, viscous friction constant. K is called stiffness. K is called spring constant. Now, what we need to do is we need to mathematically model this particular mechanical system. And after modeling, what we should get? Transfer function only, na? Yeah. So when a mechanical system is given to you, you have to draw the free body diagram across the mass or around the mass. So now I am drawing free body diagram of it. So force F of T is applied in this direction. Displacement X of T is there in this direction. And how would be the spring force acting on the body?
Opposite to the direction of motion.
Opposite to the direction of motion. And how will be the frictional force acting?
Even it would be in the opposite direction.
In the opposite direction. Is it fine? Right. So now I am drawing the free body diagram of this particular body. So I have a mass of m of t. A force f of t is applied on it, and that results in a displacement of x of t of the body. Right? And what are the forces acting? Spring force and
Frictional force.
frictional force. So spring force is in opposite direction, so which is Fk of t. And frictional force is also opposite direction. Right. So this is called free body diagram. Free body diagram means which indicates all the forces acting on a body. Now, apply second Newton's law, which says like what? Summation of forces acting on a body is equal to product of mass and acceleration. Right. So now tell me the equation. F of t is in this direction. So f of t minus
F of t minus fb of t is equals to m into dx square by dt.
Fk, very good. Fk of t minus Fb of t is equal to m into d square x of t by dt square. Right?
Yes.
Now, coming to the modeling of the spring force, Fk of t is given by
K into x of t.
very good, k into x of t. And Fb of t,
B into dx of t by dt.
b into dx of t by dt. So when you try to write this here, so f of t minus k into x of t minus b into dx of t by dt is equal to d square x of t by dt square. Right. So this is the differential equation governed by this particular mechanical translational system. Now, to obtain transfer function, what we should do?
We apply Laplace transform.
We apply Laplace transform. Apply Laplace transform and tell me f of t, f of s minus a x of s minus, tell me, Laplace transform of b, Laplace transform of d by dt of x of d.
S into x of s.
S into x of s. There is something, there is some more term, but we are assuming that is
Initial conditions are at 0.
0. Yeah, that is equal to what? Laplace transform of d square x of t by dt square.
S square x of s into.
Yeah, it is s square x of s. The other terms we are not considering. They are there, but okay, they can be added at any moment. So now we have to write the ratio x of s by f of s. F of s is equal to x of s. If I try to take common, what I will be getting? S square. There is something missing.
M, sir.
Yeah, m into acceleration. No. Yeah. So this is equal to m s square plus
S plus k.
PS plus K.
Correct. F of s minus k x of s minus bs x of s is equal to m s square x of s. Actually, this is the equation. So ms square plus bs plus, so x of s by f of s is equal to 1 by ms square plus bs plus k. Is it all right now? So this is the transfer function governed by this particular mechanical system. So model the above given mechanical system and obtain transfer function. Draw free body diagram and mention the forces. Apply Newton's second law of motion and apply Laplace transform. Right. So this is what we got. Right. Okay. Can you model the system? Take it as homework. And all of a sudden I can call any roll number and then I can ask to display your screen and demonstrate. Possible. So this is CO problem number 4.4, chapter 4 number 4.4 and page number 225. Did you download the book, CR? You bought the book or you downloaded the book? 2 CRs are there. Please respond. Correct. Benjamin Sequo. PCQO is what it is called. So it is 4.4 problem, page number 225. So now you obtain transfer function of this particular body. So we have, I think still we have 4 minutes of time. Shall we solve this or you can do it on your own? What do you say? Yeah.
Solve it, sir. We'll get more idea.
So we'll solve it so that you will get more idea. Okay, let us do word. Yeah. How many masses are there? Please interact so that you will not lose your focus.
2.
2 masses. How many
2
free body
masses.
diagrams we have to draw?
2.
2. Right. So we will try to write free body diagram M1 first. Okay. So M1. Right. So f of t is in this direction. F of t is in this direction. Displacement is in this direction. So displacement is in this direction. So y1 now. Right. So free body diagram we have to indicate the forces. What are the other forces acting on the body M1? Spring force is acting in
Spring
this
force.
direction or opposite direction?
Towards left.
Towards left. Okay, so spring force is in this direction, which is Fk of t. Right. So there exists friction between M1 and ground surface. So B1 is in y1 direction or opposite to y1 direction?
Opposite.
Opposite. So FB1 of t is in this direction. Yeah. Body M1 and M2 are connected through some friction. So FB3 is in along y1 direction or opposite to y1 direction? Tell me. When body is moving like this, FB3 will be in opposite direction, right? Yes or no?
Yes, sir.
Yes, sir.
So FB3 is also opposite direction. FB3 of t. Right? Is there any force acting on this M1 other than this thing? No, na? Right. So can you tell me the equation now? Applying second law of motion, Newton's second law of motion. f of t minus
Fk of t minus Fb1 of t minus Fb3 of t.
B3 of t.
fb3 of t is equal to
M into d square x of t by dt.
d square
Y1 of t by dt square.
y1 of t by dt square. Right. What is fb1 of t? Modeling. fb1 of t is equal to b1 into
M1G.
b1 into piston air. When piston is moving in a liquid, how we model it? It is proportional to velocity, no?
dy1 by dt.
Yeah, so b1 dy1 of t by dt, correct, no? Yeah. What about fb3t? fb3t exists between m1 and m2, right? So it is proportional to velocity but resultant velocity, right? So fb3 of t is b3 into d by dt of
Y1 minus Y2.
very good y1 minus y2. Why not y2 minus y1? Because the direct force on m1, so displacement of m1 is definitely greater than m2, right? Because there is no direct force acting on m2, right? Yes or no?
Yes, sir.
Yes, sir.
Yeah, so this is what the modeling b3 into d by dt of y1 of t minus y2 of t. Yeah, that's it. Now you know all fb1, fb3, and what is fk?
K
K
into
into
Y1
Y1 minus Y2.
Very good. K into y1 of t minus y2 of t. Right. So now free body diagram of m2. So now we will try to draw the free body diagram of m2. So displacement is in the same direction, y2 only, towards right only. Okay. Y2 of t is in this direction. What are the forces acting on M2?
Spring force Fb3 and Fb2.
FB2. So Fk of t is in right direction or left direction?
It would be towards right.
Yeah. So Fk of t is in this direction. So Fk of t is in this direction. Right. And what about FBT, FB2, FB3?
Fb3 would also be in right.
Yeah. So FB3 of t is also in this direction. But what about FB2?
It would be opposite.
It is opposite because when body is moving like this, it opposes. So FB2 is in opposite direction. So FB2 is in this direction. So this is FB2 of t. Correct, no? Is there any other force acting on M2? No.
No, sir.
So already you know what is FK and what is FB3. Already we have seen the same thing is in substitute. But what is FB2? B2 into d by dt of y2 of t. Rest all you know. Yeah, now what is the equation here? Fk of t plus
Fp3 of t
minus
Fb2
is equal to is it understood now?
yes
Okay.
sir.
Yes, sir.
Yes, sir.
Yeah, so now you drawn free body diagram of M1, free body diagram of M2. Okay, and then now you have all the terms. Now you just substitute, and now you can obtain transfer function y1 of s by f of s. Do it now and be ready with your answers. We will meet in the next class. If you have any questions now, you can ask me, or otherwise we can leave. Do you have any question? Yeah. If you are not having any questions, so we can stop today's class here. So thank you.